Tyramine is an indirect-acting sympathomimetic trace amine. It occurs naturally as a byproduct of fermentation, commonly found in aged cheeses and red wine. Under normal physiological conditions, dietary tyramine poses no threat to the body. It is consumed and processed without affecting the sympathetic nervous system. This protection is maintained by a metabolic barrier. Monoamine oxidase, specifically the MAOA isoform in the gastrointestinal tract and liver, intercepts the tyramine. It catalyzes its oxidative deamination, breaking the molecule down into inactive fragments before it reaches systemic circulation. This safety mechanism fails when a patient is prescribed monoamine oxidase inhibitors, or MAOIs, which are used to treat certain forms of depression. These drugs deactivate the primary gastrointestinal and hepatic MAO enzymes, removing the metabolic shield that usually neutralizes dietary amines. Without this barrier, tyramine from a single meal absorbs directly into the bloodstream, achieving high systemic concentrations. Once tyramine bypasses these initial checkpoints, it circulates freely with direct access to the internal machinery of the sympathetic nervous system. To understand the resulting Pressor response, we must follow the tyramine out of the bloodstream and into the microscopic presynaptic space of a sympathetic nerve terminal. The outer neuronal membrane serves as the first physical boundary of the sympathetic terminal, separating the extracellular environment from the internal cytoplasm. Spanning this membrane is the norepinephrine transporter, or NET. While its physiological role is the reuptake of neurotransmitters, its structure provides a pathway for the tyramine breach. Because of its structural similarity to endogenous norepinephrine, extracellular tyramine utilizes NET to cross into the neuronal cytoplasm. This specific entry mechanism defines tyramine as an indirect-acting amine. It does not stimulate external receptors. Instead, it enters the neuron to trigger a response from the inside. Once inside, the tyramine must bypass the terminal's internal chemical defenses to exert a physiological effect. Inside the nerve terminal, the cytoplasm contains mitochondria, which house the next layer of the neuron's metabolic defense system. The outer mitochondrial membrane is lined with MAOA. This enzyme acts as a homeostatic barrier, rapidly deaminating free cytoplasmic norepinephrine and any foreign monoamines that enter the cell. Under normal conditions, tyramine is caught in a race against this oxidative deamination. Mitochondrial MAOA is so efficient that very little tyramine survives long enough to reach the storage vesicles. In the presence of an MAOI, however, these mitochondrial enzymes are inhibited. With the internal degradation pathway stalled, intact tyrine molecules accumulate rapidly within the cytoplasm. This blockade also causes free cytoplasmic norepinephrine to build to concentrations far exceeding its normal steady-state levels. The failure of this secondary metabolic barrier leaves the neuron in a state of chemical overload, creating the pressure required for vesicular displacement. The overflowing cytoplasmic tyramine now moves towards its primary target, the internal vesicles that store the neuron's neurotransmitter supply. Tyramine utilizes the vesicular monoamine transporter, or VMAT, to infiltrate these storage compartments. This storage system is inhomogeneous. Most of the terminal's norepinephrine is held in a large reserve pool, but a small fraction is partitioned into a cluster docked directly at the active zone membrane. This docked cluster is the readily releasable pool, or RRP. These vesicles are molecularly primed and immediately available for exocytosis. While the larger reserve pool is resistant to tyramine due to a slow transfer rate, the small active RRP is highly vulnerable to immediate displacement. High concentrations of tyramine utilize VMAT to enter the RRP, where the molecule begins to compete for storage space. The incoming tyramine physically displaces the stored norepinephrine, forcing it out of the RRP vesicles and into the already saturated cytoplasm. By displacing the neurotransmitters in the RRP, tyramine creates a localized high-pressure surge of free norepinephrine within the terminal. Simultaneously, the cytoplasmic tyramine activates an internal signaling pathway. It binds to the trace amine-associated receptor 1, or TAAR1, which is localized intracellularly within the presynaptic terminal. Tyramine acts as a high-affinity agonist for TAAR1, initiating a G-protein-coupled signaling cascade. This binding leads to the activation of adenylyl cyclase and the rapid accumulation of cyclic AMP. The signaling chain continues with the activation of protein kinase C, or PKC. This cascade culminates when PKC phosphorylates the membrane-bound norepinephrine transporter. This process bypasses the classical release pathway. Instead of calcium-dependent vesicle fusion, the release is mediated entirely by the transporter itself. Driven by this phosphorylation and the massive internal concentration gradient, NET operates in reverse. It expels the cytoplasmic norepinephrine outward into the synaptic cleft. This transporter-mediated efflux floods the synapse with norepinephrine, causing the peripheral vascular pressor response observed in a hypertensive crisis. This hypertensive spike results from a mechanical reversal of the transporter, forcing the terminal to purge its neurotransmitter stores into the synaptic space. This data tracks the blood pressure response to repeated tyramine exposure. Following the initial spike, subsequent doses produce a rapidly diminishing effect. This rapid decrease in responsiveness is known as tachyphylaxis. The kinetics of this decay are determined by the physical limitations of the readily releasable pool. Because the RRP is small and the transfer rate from the reserve pool is slow, tyramine exposures quickly exhaust the active norepinephrine supply. Beyond the depletion of the pool, tyramine establishes a permissive blockade within the remaining vesicles. As the RRP is emptied of norepinephrine, tyramine occupies the storage sites within the vesicles. Tyramine now functions as a pseudotransmitter. It occupies the vesicles, preventing newly synthesized or recaptured norepinephrine from being stored for future release. Tyramine's mechanism is inherently finite. The same processes that trigger the hypertensive spike also exhaust the terminal's active supply, faster than the biological system can replenish it.